We talked about different types of flow, laminar and turbulent flow. And then I talked about how laminar flow increases when laminar flow deteriorates when you increase the speed, or when you decrease the viscosity. We talked about this idea of dimensionless numbers, which I think is one of the most beautiful concepts in the world. When I discovered it, it blew my mind. The idea that this is what you need in order to scale a physical model. You need a quantity that is that you can um, divide by another quantity and get a ratio, and you experimentally determine whether that ratio is consistent across scales. And if it is, then it essentially doesn't have dimensions, it doesn't have scale. And you can use that to build a model. You build a model that keeps those parameters small, the same in the small model, and you can match those parameters to the big model. Then you can use a model to simulate flow. And we talk about Reynolds number, which is the number that describes the characteristics of flow. So that has to do with basically how big something is and how fast it's going. U is how fast it's going. I always use U. And the L length scale is just the length of the phenomena that you're measuring. And then mu is the viscosity, the dynamic viscosity. And that is something that you measure, and that you cannot change in a wind tunnel where you can't control the temperature or the density. The Reynolds number just gives you is just a criteria you can use to apply to any particular situation. So you can just apply, you can say something's this big and going this fast. It has in this type of material, it has that type of Reynolds number, and then you can predict whether the flow is going to be turbulent or laminar. Almost all flow is turbulent. And then I talked about volumetric flow rate, which is how much air is traveling through something. So that's just the volume of air that's moving through something in a given time, which also, if you think about it, since volume is area times the height, it's also the area of the cross section times the speed, since the length times the t. That would be not actually true. You would have to take d to be x to be very, very little and t to be very, very little. But essentially, that's how that is determined. And then the mass flow rate is just that times the density. And then I talked about the continuity equation, which is the idea that in a pipe, you have the mass flow rate, the amount of air is the same. And so in order to figure out how much air speeds up, you just can use the air ratio of the areas, because the same amount of air has to be going through this as that. And I talked about the boundary layer, which is how at the edge of things, because of frictional forces, stuff gets all screwed up. Air gets caught by the friction. And I talked about flow uniformity, which is what we're trying to achieve. Okay, and then I talked about the wind tunnel. So at the end of today, I'm going to post a thing at the end of class, and we will sign up, for a part. And these are you'll sign up for the parts that you're going to work on, and then you should set up like a 15-minute meeting with me, and we can start to get to know each other personally, if I don't already know you, and then we can also talk about what is the thing that you will test. So we can do that on Zoom anytime during the week. It'll just be just to have a individual conversation, or maybe we'll do it in class if there's time at the end of class, about what are the things that you would get going on in terms of testing this part. Okay. The other thing that I did is, I don't know why this slide is here. It shouldn't be here. I made a budget, and I asked Grace for the money. So we got $1,900 to build this thing. Okay. So that's what we're going to do. So all of these things I am going to order. So hopefully this will mostly cover it, and we won't have to spend things other than on individual models. Okay, so um, why is this interesting to me? It's interesting because it's very much like, I mean, I kind of wanted you guys to do this, but it'd be ridiculous. This is, I mean, maybe if you guys have experience working in projects and things like that, but if you don't, this is very much what it's like, right? Like going online and pushing around for the different parts. Okay, so what I'm thinking is um, maybe this is too thick. We might order a 1/8 one. This is the copper tubing that we will use for. So whoever signs up for that at the end of class, I will give this to you. Okay, and you can go and see what you can make of it. All right. And then this is what we will use for the thing that the air will pump through. And then Burton and I had a long conversation about this, by the way, and he will, I've sort of updated the thingy, this file, which I'll also post at the end of class. And basically, these are just going to be plywood, and whoever's designing that will give Burton a cut sheet, and he will help you cut the plywood in parts. And basically, it will not be a frame like this. It will be like a board. It'll be made of boards that'll be double laminated and put together. So it should be pretty easy. There'll be straight segments like that, and then we will bolt them together. I hope that makes sense. This will be like a bar and a bar and a bar and a bar, just straight pieces of plywood that'll be bolted together up and down the side. We will make the thing out of this. It'll be this exact thing, except whoever is working on that will, you guys can pass it around. These are skinnier, these are thinner. Some I just had long. We can test this on this stuff. We can test our joints. We can test various things. But then we will order 48 by 72 sheets and of that thickness. And we will Zun cut them. And it'll work very well, I believe. Okay. There'll be these little fold over joints, and we'll just fold them over. And then I like to do this, by the way. I like to give you guys toys. Okay. These are toys. These are my toys. By the way, I'm telling you, I'm done. I'm done with my part. The rest is up to you guys. All the materials, give you the toys. We will use this. This is aluminum foil tape. Isn't that cool? Look at that. And then I will buy a big sheet of this. I think this is I don't know what this is. This is uh yeah, this is neoprene. This is our squishy insert. It's a rubber insert, and so we'll buy a bigger sheet of this, but it'll basically just be strips like that. And then this is what I think is really cool. This stuff is super cheap. So cheap. This is like the film that you put on cars. Like it's like if you want to like fix your car with something really cheap, there's like black sticky back. So we can use this stuff inside the chamber in here. We can line it. I'll buy a big sheet of this, but we can see if it works. This cost $6. Bought a tiny little thing of film for that. And then this is the gaffer's tape. Okay, so this is if we have this is for fixing black themes on the inside, and also for doing stuff with the um, smoke machine. If we need tape, the stuff's very sticky, very easy to remove. And then this is the tube. When we check out our wind tunnel, when we check out our smoke machine, what we can do is essentially we can find out if this fits in the hole of the smoke machine. Like that. and we can rubber band it on, and then we can squeeze it with this. And if we pull it tight to the hole and tape it with gaffer's tape, I think the smoke will go through there. And then um, we'll have another one that will go into the 3D print on the other end. And that 3D print will connect to this, which will be sticking out of it as closely as we can get. So Burton thought I was kind of crazy. He thought I should just buy ductwork rather than doing it ourselves. But that would cost a lot more. Right. And they don't sell these parts. Every wind tunnel is custom. It's much, 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 much too big. And so I'm pretty confident that it's going to work. And I think it'll be interesting. I have some ideas about these joints. I think what we'll do is if you look at this, I've panelized this into three parts. We might switch it into two parts, but that unrolls to that. Okay. So basically we will have like there'll be a little fold up here and a fold up there, and we'll bolt them together, slide it in. There'll be a notch here. This will slide through, and we'll bolt it to the next one, and then we'll cover it with aluminum. So it should be. I think your part in terms of the design is going to be dealing with the thickness of things, because I think that's useful for students to have to deal with. So I will give you the model stands thickness, and you will offset things and make the bolt holes and stuff with my guidance, and then we'll do that. Okay. All right. So we got materials. I will. Oh, the fan. I ordered a fan. I look. Thank you. You sent me like Miles sent me like what's it called? Yeah. Let's look at that for a second because it's fascinating. A regulator, okay, which um, this thing, which you can plug in and regulate the power. Although I think I didn't go with it because I think it got very complicated. Like apparently, like you have to make sure that the power supply to the fan like is like not like a binary switch or something like that. I didn't understand it. I couldn't I talked to the fan people who make these things, and they kept being like, we don't recommend that. It already has step levels, and there's like that's like I think you need like a certain kind of current in order to make it work. I don't know. I didn't understand it. It was a little over my head, but it was a good idea. And I think I probably could have found a fan that would have worked with it. But instead, I bought this fan. These are all the fans I looked at. I bought this fan. Oh no, I didn't buy it. That's not the one. I bought a yellow one that has a stepless speed switch on it. Yeah, it's already got one. It's got so that is coming to Home Depot right now. It'll be there on Friday. And then I believe we have enough stuff to test all the joints already, and I will order a large sheet. And whoever is signing up in the things, I will distribute the materials. You will have giant things sitting next to your desk. Like you'll have a big sheet of aluminum, if that's okay with you. I mean, I can keep it in my office if you don't want it, but then you'll have to come get me to get it. So like we might just you might just keep it and you'll work on your part. Okay. Does that make sense, everybody? Questions about that? I don't know if I've described it well enough. I feel like maybe I won't. Maybe we'll just meet individually about it. Oh, these are hilarious. It's just I looked into this so much. It's really just bug screen. Like I was looking online and it was like I was gonna like trying to order like a steel mesh and everything, and it's so expensive to order a steel mesh. But actually, what we need is the wires per inch just have to be like a certain amount. That's what I was putting this in. This is what the metric is, the wires per inch, and also the porosity. And the wires per inch is just how many wires there are per inch. And then the porosity is obviously the thick is the how many wires there are per inch minus the thickness times how many wires there are per inch, then squared because it's in both directions. And that's the porosity. So turns out bug screens have 70% porosity and they have 20 by 20. That's how they write it, 20 by 20 uh, wires per inch. So we can use bug screen. So I ordered some $10 bug screen, giant sheets at the Home Depot. And that was not at the home. They didn't have it there. They had it in Everett where the fan is going to go. So I'll go to Everett and get the fan and get that. And then I don't know how we're going to attach the fan. That's something we're going to have to look at it with the aluminum and see whether or not we will. I think we might. I want to be able to take it out is the thing because I feel like it'll be unwieldy if we have to carry the attachment on it. If we can't take it out, we'll just rivet it in because that'll be easy. We can use blind rivets so we won't have to reach our hands in the fan and it'll be easy to attach permanently. The other option is we could like make little hooks on the fan and have little claws on the tube. Like essentially, let me show you this. Actually, let me make this clear. Um, Basically, the way this is going to work is these will be this is too long, so these will slot in. They'll slide in. They overlap like that. And then the last one has to overlap the fan. And then we just have to look at the fan and see whether the fan has any way to attach this easy. And if it doesn't, we'll just rivet this part along onto the fan at the end, which I think will be okay. Okay. So I will distribute this at the end of class. It'll be more organized. I'll put I'll unroll the files in a line and I'll put the thing there and then you can all just take your part. Right? Okay. The next thing that I wanted to do is something completely different. Totally different. Which I hope will be somewhat exciting for you guys. Essentially, I hope I can do this. I hope I can do this. All right, I want to talk about natural ventilation in reality. Like I don't want to get into how to accomplish it or the math of it at all. I just want to talk about it like practically in real buildings. And I want to give you examples from the history of natural ventilation and talk about that. And I basically, from the examples that I choose or other things that you like from the architects that I give you, I would like you to select two, maybe you'll just do one if it's interesting enough, precedents that you will work on. And essentially you will model, you can get going on modeling a section of that precedent that you can build, you can use for your simulations and your actual your physical models. And what's cool, the other thing that's cool is a lot of the precedents. Well, I'll tell you this in a second. I'll get to that in a second. Okay. So what's interesting to me, I want to see if I can convey, you guys have probably all seen this slide from me like many years ago. Want to see if I can convey a little bit of the climate around these things, which is, I think we need to think about natural ventilation in terms of traditional typology. And one of the things that was interesting, Moneo, I wrote this article about typology called On Typology in, I think it was in 1972. And he talked about how traditional typologies are these. They're vernacular things. Basically, from Moneo's point of view, typology is almost synonymous with the vernacular. It's something that grows up in a specific context, in a specific uh, climate, in a specific set of uh, um, material systems for a specific set of social customs, and and then he believes that we don't have typology anymore because we're in a world where we share everything across cultures, and also where the traditional climate isn't quite controlling, the local materials aren't controlling the way we are building. And so he thinks we're in this kind of post typological universe where we just reference things and sort of make collages out of typologies, uh, out of parts of typologies. Okay. A sort of a different idea of typology is Aldo Rossi's. And his idea has a lot to do with this notion of elevating the daily encounters to the extraordinary. So it's like something like the bicycle thief, like Italian neorealism, where you sort of there's something you encounter in your regular everyday life, but that thing is almost like distilled and elevated uh, from the quotidian into an exceptional event that stands for all of the uh, all of its instances. And so I think that the first part of natural ventilation that we have to talk about uh, really is here. It's really traditional vernacular typologies that are from specific contexts, and that is almost from the 1100s through to the beginning of the 19th century. The local buildings of any particular place are largely driven by needing to naturally ventilate in that climate. Okay, so I wanted to say just a couple of general things. So basically, air does not move. Air moves from positive to negative pressure. And we will talk about pressure at length. I will talk about stack effect and how that actually operates. But it's either moved by wind getting blown, which is just the force of the pressure of the wind pushing it, or it's moved by basically buoyancy. And buoyancy really is just hot air is less dense than cold air, and so it has less pressure, and the air moves from the positive to the negative pressure following the following excuse me following the temperature gradients, because a particular area is colder than another area. Okay, and so then there are sort of certain kind of like natural resources that sort of get used alongside of the motion of air, and really they have to do with water or the ocean, the placement of water, uh, and vegetation and topography. Okay, so it's kind of like, and also the ground, because the ground is a temperature sink. So there's really four, in addition to the wind. The air picks up speed over the water. So if you're next to a big body of water, the air is going faster. And also, the air is colder because it has water in it. And we'll talk about that in a little bit. And also, when the air goes through vegetation, it is also colder because it is shielded from the sun. And so that creates a temperature gradient, and it also slows down the air. So Water speeds up the air, creates a temperature gradient. Vegetation cools down the air, slows down the air, and creates a temperature gradient. And the same thing happens with the land. You have a hill, air speeds up when it's going over it, and gets separated around it. And just like in a wind tunnel, gets sort of compressed into smaller areas and ends up going faster. And also, um, air typically picks up moisture on the convex sides because of their, um, in shadow. And then when it gets in the sun, heats up and precipitates. Okay. So there should be another slide in here. Excuse me. It might be later, this other slide. Okay. So, I wanted to then just show you some of these vernaculars. There's a slide in here that's not supposed to be. I'm going to take a second and find it because it's very helpful. Okay. Um, well, uh, it doesn't matter that I don't have this slide because I will go to the actual essay. Okay, which is that's a good breaking point because I put it up here, um, essentially like I'm uploading zillions of case studies. Okay. So in the last, um, 30 years or whatever, people are doing tons of CFD analysis and wind tunnel testing on some of these buildings. And many of the precedents that I'm giving you, somebody's done a study on it. And so we can look at that and see whether or not we're sort of conforming to it or not. It'll be a guideline for that. And also, I have a very helpful essay, which is um, uh, sometimes I find it very helpful to find review articles. Okay. So review articles are very helpful. They are surveys of the literature. When you are doing your own research, surveys of the literature are extremely important, okay, because they give you links to, they're not original research. They give you links to, and they just survey and comment on the things that people are writing about, okay? So essentially, this one that I will post for you has um, it categorizes all of not all, but many of the essays that have been written in the last 30 years into which sort of typology of natural ventilation they are talking about. And so I think these things, they correspond to really vernacular types. Okay. So there are courtyards, um, and then there are what are called cold lanes. Okay. And then there are stilt, things that are raised up off the ground. And then there are things that are using the earth. And then there are things that are using the shape of the roof. So let me just kind of explain this a little bit before I move on and show you examples. So a courtyard, okay, there's a lot of debate over how a courtyard operates. It can operate in two ways. It can either, it can either block the sun and that in so doing cool down the, or it can expose itself to the sun and block the wind and in so doing heat up the air. And so depending on which climate you're in, they're used in different ways. And that can be helpful because sometimes you have two courtyards and you end up with a hot courtyard and a cold courtyard. And the hot courtyard and the cold courtyard end up creating a suction effect where the air moves through from the cold to the hot because of that. Okay. And so then there are what's called a cold lane, which is kind of like a very small courtyard or anything cold, like like um, if you're in a room and there's like a porch next to you, or like a corridor that's kind of exposed to the air, it will be colder than your room. And so if there's the possibility of air movement between those two things, the hot air will follow. So ventilation will just be created by the presence of something cold next to something hot. The air will move. The hot air will move out into the into the into the cold air in that way. Okay, and then when you raise up something, it creates an area underneath where the air speeds up, and that can end up um, also being ventilated through the floor. That's very common. When you put something in the earth, often what happens is there is a um, like a pressure difference between these two places because this is higher and this is lower. So we'll talk about that later. But when something is higher up, there's typically a pressure difference from when it's lower. And so the air gets sucked through. And as it's getting sucked through, it gets cooled down by the earth. And so that contributes to a temperature gradient, which creates a more air movement as it develops. And then sometimes you shape the roof, okay? And that's like an airplane wing. The air will go faster over the curved surface than it will go like through the building if something is open, like if there's a porch here or something, and the air is traveling faster over the roof and slower over the bottom, then it creates a pressure difference from the top to the bottom, and that pulls air out. So you can do it with shape, and you can do it by making something narrow, or you can do it with or making something shaped, or you can do it with a temperature difference. Okay, so and I'll go through these again when I talk about the specific things. So, but all kind of vernacular architecture essentially works on these principles. Okay, so if I go back to my slide presentation, these are still dwellings. Okay, so there's many. Um, uh, this is in Myanmar. The vernacular housing is lifted on stilts so that the wind can go underneath. You can store things underneath when it's cool, and there can be holes in the floor, and that will ventilate the air. And so are these. These are the Minhasa, which are also they're in Indonesia houses, and they work on the same principle. And so I think these are very simple to look at, and I think but they're quite beautiful because you can see the way the environment is sculpting them, and I think it would be easy to pick one and model it. These also have vents up top, so many things are sort of combined. So like you end up with cold air going under below, and then there's holes in the floor. And since the air is moving faster down here than here, and this is colder than in the house, that creates movement of air into the house, and then the hot air in the house rises, and there's a vent up here, and it shoots out. So essentially, the temperature difference and the movement of air contribute to each other and help each other out. They go along with each other. These are in Dao Lo. There's many stilt dwellings all over in different communities in China, and actually they're still considered some of the most comfortable housing. So a lot of these are very current, and people choose, I think, these over other ones. So I think I put up an essay. It's quite wonderful. There's one that has like the plans and the section of these houses, and you can see, like they do a thermal analysis of it. So you select something like that, you can read the thermal analysis of it. It's there, and then we can see if we can match our emotions to the motions of that. Okay, these are I think um, uh, in also in Indonesia work by with a very different principle. I feel like I'm missing a slide. These like have um, uh, uh, no windows in them, so the air you know heats up inside and just goes out the top, and then it has a kind of a porous um, uh, uh, surface, and that creates leakage, which helps the air distribute itself. And this is why. One second, guys. I'm on the wrong one. There's two of these. That's why I'm missing some slides. Okay, much better. Um, all right. Here's my thing. I brought those together for you. Okay, so they're in one spot. You don't have to look at the original essay. Also, another house in Indonesia, and then another stilt dwelling, not by the water, very beautiful. And then also, this is the picture I wanted. I just find that so stunning. It's interesting to me how much shape is controlled by these forces. And what I have found that is um, exciting is when you look at the world through the lens of one particular viewpoint, you end up seeing it in a totally different way. So for some reason, the things that we usually look at have no relevance when you look at the world and through the lens of just how the air moves. And suddenly, like a very narrow lens reveals sort of hidden things. So I think that's exciting. These are made of bamboo, and the air sort of weeps out of the gaps. Okay. These are in Sistan in Iran, and these are in Turkey, on house in Turkey. And these work on the shape principle. Okay. They have a round roof, and so the air speeds up as it's going over the roof. And then there's a little hole in the top, and the speeding up air uh, ends up sucking air out of the little hole in the roof. So these are the shape vernacular. This is from this essay that I put up, uh, natural ventilation in Sistan, Iran. And you can see they've done like a CFD analysis. By the way, it's funny to me how, in a way, useless sometimes they are. And we will deal with that. But you can see how it's working, right? You can see the wind picking up speed as it goes over the top, and the speed of the wind going over the top, drawing the air out through the little hole, which I think is interesting. I do think it'd be possible just to look at the early 1700s American vernacular. This is what this book that I mentioned before, The Uses and Abuses of Air, is about. And that these rooms have very low ceilings, and in order to kind of keep the temperature from escaping to the point where it's not around your head. And then they would have vents often in little holes in the ceiling and in the floor, or a hole up at the top of the flue. And that's because what would happen is if you turned on the fireplace and it was hot, it would just pull air out that was cold all the way at the bottom, and the air where your heads were would just get stale. So you had to put a hole higher than your head in order to have the air that was up here actually pulled out as well through the flue. So uh, otherwise, it was like suffocating in older houses. So there's often holes in the ceiling, or holes in the flue. I also we're not gonna analyze this one. I think it's too complicated. But it also, these old kind of churches and mosques work on these principles. They have high windows, and the high windows, the air is able to. Sorry. I've been able to find an essay analyzing the natural ventilation in this. Keep trying to. People always talk about it, but I haven't actually found somebody who's done an analysis of it. It seems to me that it would be incredible to look at because there's this very large courtyard with a huge arch and this huge funnel, and I feel like the wind would blow in. And then there's these high windows up top, and those high windows should create a temperature gradient that would allow the air to, to also be contributed to that. And then there's these tall turrets too. And I think people have talked about retrofitting those. I don't think they actually were. People have talked about retrofitting them also for air issues. So I think it would be incredible to look at that section in from the point of view of trying to figure out how the air moves in it. The only thing is the thermal mass has a big contributor to that, and that is something that we will have trouble dealing with. The way in which surfaces heat up and cool down is something that's very hard to incorporate into a simulation, and it usually people don't do it. But if you don't do it, you kind of get inaccurate results. But we can talk about that. Then there's these Horeos in Spain. These are grain um, storage, and they're lifted up to be free of moisture, and it rains a lot, so they need to be porous, so the wind blows through, and um, little holes, and cools and ventilates the grain uh, all over the place there. And then there's this Pueblo, this very old situation, which I think has a very wonderful idea. It's very sort of intelligent. Essentially, um, there would be an inlet here, and they would have a fireplace. You would go in the entry there. People have done archaeological studies of this, and everyone used to wonder why was there this other hole with no access. And essentially, it would draw um, the temperature gradient in the space from the fireplace would create a suction of air out, and that would draw fresh air in through the hole. This would be, oh, this is terrible. So sorry. This would be heating, this would be hot. And so that would create a temperature gradient, and the air would be moving. By the way, it's not just that air rises, the hot air rises. It's that when you have a temperature gradient, it creates a pressure difference, and that creates a continual flow of air. So that would create a suction where the air here is moving out, and then cold air, fresh air over here would get pulled in and over here, replacing the air in the place. So you can be underground and warm because this partition blocks you, and you can have fresh air from the outside because the fire is creating a current, which is pretty wonderful, I think. Okay, then there are the wind towers and yachts, and the wind towers are all over the place. They're in Iran and in Egypt and in the Arab Emirates, and nobody knows who invented them. There's archaeological evidence of them back from the 5th century BC. But they're amazing devices. They're basically, air conditioners in the past. And they are many different kinds. So these are most of the impressive ones are in yachts in Iran. And there are different sided ones. There are many sided ones, and there are two-sided ones, and there are one-sided ones. And they all work differently. Depends which direction the wind is blowing in, and whether the wind is dusty and carrying dust with it, or whether sometimes They have pools of water next to them so that that cools the air. They all work differently, and there's many different studies on the different properties of the way that they work. But essentially, that's a one-sided one, right? So sometimes when you have a one-sided one, you actually face it away from the wind because usually they face at the wind and the wind blows into it. But sometimes you face them away from the wind, and then there's a negative pressure over here because the wind's hitting it over here, and so it sucks air in anyway when you turn it around the other way. Um, they're really very different and interesting. And then these little holes on the roof are not part of them. It's just another way to vent. So this is usually there's like a interior room below them that's very large that the wind tower opens into. And so that's just to get rid of the hot air that doesn't go out the wind tower. But these are all the types, okay? So they're divided on the inside. So they're divided usually with many little divisions, which are just kind of aesthetic, and then major divisions. And the major divisions are to deal because there's usually an inlet and an outlet. One of the air, the wind blows in here, goes down, and then there's an outlet for the air that's going out. So whatever direction is facing the wind, the air goes in, and then air comes out the other side, and that turns over the air in the building. So there's usually like a big fin going all the way through it. And they look like this, okay? There's like these fins on the inside dividing it up into chambers. And it depends, right? If you have many chambers, obviously less air can get in, but also if the wind changes direction, it's less sensitive to the changes in the direction of the wind. If you have two chambers, it's more sensitive. So there's all different kinds, okay? And these are how they work. There's a big room, and then there's usually like a side chamber, and then the turret, the wind catcher, feeds right there. Okay, it's right here off to the side. So there's a large central sort of room that is the main living space, and the wind catcher blows air into it and also takes air out of it on its two different sides. So they're like this. Okay, so the blowing wind creates a positive pressure over here and a negative pressure over there, and that means the wind goes down into the room, and then the negative pressure sucks the air out of it. And it changes depending on how fast the wind is going. If the wind's blowing really fast, it basically just blows wind in. And if it's going much slower, there's more of a chance for the air to turn over and just be affected by the temperature gradients. And sometimes they're connected to these qanats, which are tubes underground filled with water. And basically, it's hot in here. So the hot air rises up, and that helps. So that the hot air rising also helps and contributes to the way with the wind. So the wind and the hot air forces help each other. And then this is hot, so it's got low pressure. The air rises up. And then this movement of the air also draws air through the underground tunnel, and that air cools down as well. So it's a way to keep the interior cool. And we also have examples of people trying this out in different situations and seeing how it works. Sometimes they are coupled with what's called a solar chimney, which is like, it's the old version of a double glazed facade, which is where the air is heated up by the sun in the glass volume. And in the summer, you open the top and that pulls air out. And in the winter, you close it down and it becomes like an insulating thing. And that often in the wind catcher, there's also like wet pads in here, and the air cools down as it's coming in here, and then this air is heated up, and that increases the flow. And there are studies of people trying to do this with a physical model. Okay, this is not old. This is like new. Like somebody like putting like the people in yachts like to do this because they live around these things all the time. So like putting aluminum foil here as an insulator and heating it up and trying to measure whether the air is going to move, and then comparing that to the CFD analysis and seeing whether you can get your results to go alongside each other. Which I have to say, like I just love how nobody knows, and you have to check it in every situation. It's like the most. It's a little frustrating, I would imagine, because it feels like maybe it's just all a bunch of words. But um, uh, I think this thing of pressure and the way air moves is like a little hard to get your head around, but it's always the same thing over and over and over again. So I feel like once we talk about the pressure issues and talk about the way it works practically, that'll feel very comfortable to you. I think it will. And then this other idea that everything is still open for discovery, I think should be empowering. Um, okay, so that's with two of them. And then I think I have an essay about this particular mosque that has both the wind towers and the shape, which I think is seems very exciting to me, that it has both the round shape and the wind tunnels. I feel like that I don't know what would happen. It just seems exciting to look at it to me. Okay, then there used to be in Hyderabad in Pakistan, there used to look like this in the 1700s and 1800s. There were wind. The whole city was like, used to be called the city of the wind. Um, it looked like that. Wind catchers on every single building. It's not like this anymore. And it's not like this because of pollution and also air conditioning making it not necessary and also making them not work correctly. Looks like that now. But still, I mean, it's fascinating to think how incredibly uh, widespread and necessary such a phenomenon was. Um, and they're also in Britain, in Kent, they have these, which are the same. It's the exact same thing. It's the shape and the wind catcher, although these face in one direction. Okay, and then there are these. Um, I have another essay about these sort of courtyards in the earth, and the way there's these are in Yaodong in China. There are little rooms off of each of these, and there's an entrance somewhere. And basically, this, it cools down the air in the courtyard as it faces the earth. And then I think the traditional, um, uh, you know, there these this is in Beijing, a traditional house in Beijing, but in Hui, I don't know how to say it in Hui, how they're supposed to be a little bit more about ventilation. But essentially, the whole house is based on a ventilation principle. There's a gate, and then there's another gate, and this gate has holes in it so the air can blow in, and there's usually an open room under here. And so the air can go through that open room, and then the bedrooms are here, and there's like a breeze going through the whole house, um, like this. So there's an open courtyard over here, and then there's a door and a screen, and that creates a breeze through the entire house. And the way they do this, okay, the way people do these studies is literally like this, okay, like you go with smoke and you see where the wind is moving on the site, and or you do it with a smoke pen or with a ribbon, and you take points, and then you can put that into the input conditions in the CFD model and try to uh, because you don't know the most confusing thing about making a model is the boundary condition. You don't know what's around it. So you have to, it's a complicated universe around it, and you're trying to isolate something. So people usually go and you figure out where the wind is moving around it, and you can put that in the model, and then um, you can check it against the physical reality. So most studies are done against real things, so that we can validate our models rather than on new things, because if we do it on new things, it's very hard to predict whether we're doing it right. So this works on two principles. So the patio, the main hall is ventilated by virtue of just the wind blowing through it. But even the bedrooms that don't have an opening on the other side are ventilated because they have a screened partition and high windows that can be opened even if they're not, even if the door isn't open. And there's an area over here that is open to the outside more directly. And this is what I was saying before. So this is cold. And so since that's cold, it creates air movement against the hot bedroom. So it's both. This is an example of a cold lane. And then these courtyard houses are very interesting. Essentially, the courtyard is hot, and right next to the house, everything's built very close, and there's deep overhang. So there's these extremely cold streets in between the buildings. And those cold streets, if you open up small vents to the cold street, it creates a current through the hot courtyard, and that will draw air into the bedrooms directly and move it through the entire house. So that's just a model of the whole city. These the streets, because they're narrow, the wind also goes faster. So there's both wind pressure through here, and it's very cold because it's in shadow. And if you make holes, it creates a thermosiphon through the entire house. Something like that. And so this is the way this is typically done, because modeling the whole thing is almost impossible. So people do it in cross section. You can see the air getting sucked through from the street and dispersing itself throughout the house in that way. And that's the different. If you don't make that hole, then you end up with just blowing air in the front door, and blowing air in the front door will only, cool off the front row. Whereas this pulls it in through the hot spaces first, and this is always going through one space. Okay, these dragon houses work on the same principle. They work by creating these cold spaces next to courtyards so that you can create air movement that way. And also, so do the palazzos, the Italian palazzos. They have like two courtyards. And this one and that one can work in dialogue with each other. I think the greatest example of that are these the courtyard houses in Damascus in Syria. They don't always, but many of them have this two courtyard principle. There's about 12 of them that are very famous. There they are. They have like a hot courtyard and a cold courtyard, like I was saying before. The hot courtyard gets sun and is open in the direction of the sun and is wide and big. And then there's one also that has water in it and a fountain, and that cools the air down. And the two of them in dialogue can create a thermosiphon and move the air back and forth. And then they also have screens, which is just like, by the way, it's just like the wind tunnel. It's to sort of make the air uniform as it passes through the screen, and also to give you privacy while you're still getting natural ventilation. So that's why you have all these beautiful screen work. It kind of smooths the air out and also allows you there to be security while also allowing the ventilation to work all year round. This is the very, very famous house in Oman. It's like the most famous building in Oman, and it has a similar situation with a courtyard in the middle and cold lanes, and there's a very in-depth CFD analysis of it. So I think it's an interesting example that we could build on. Okay, then there's I'm leaving the vernacular now. Okay, so that's the vernacular. Okay, so basically that's like from the 1600s through like the early part of the 19th century. There's just vernacular dwellings, and they all work basically based on the principles that are necessary for the local climate. And then I've organized this almost entirely chronologically, which I find it confusing when things are done thematically. I feel like I wish I knew how things were done chronologically. So I've tried my best to do it chronologically. Okay, this is the Pitti Palace in Florence in 1458, although it was continually being modified for a while. And this is very similar. Okay, there's a very hot area in front, this super hot courtyard, and then behind are the Boboli Gardens, which were designed for the Medici in the 1700s in 1766. And they are these very luxurious gardens with fountains and trees. And so obviously there's cold air back here and hot air out front. And that causes air to move through the building. And then there's this giant pit, and the air goes down into the pit and cools down even more. Um, and you can see it. Look at that. It's like a giant air conditioner. Like it's like the coolish air is coming down here and cooling down even more, and then getting pulled through the building because of the hot zone out here. And by the way, there's also a very famous grotto there, which you would go in and like to cool down. It's in the earth and has water in it. And it works like this. Like so the cool air gets pulled through the building from the basement up. And this is somebody doing a doing a model of it. They used uh, dry ice to simulate the motion of the cool air up through the building in that model. Okay, I'm not crazy. People do this all the time. It's totally normal. And then they do a CFD analysis and see if it conforms. See how fast the air is moving in that area. These are very famous. These are the Aeolian villas in Costanza. They're from the 16th century. There's 6 of them. They're very, very, very famous, and they are these sort of fancy Italian villas, and they are connected to caves. And basically, the air there's a pressure difference because this is higher than here. So I haven't talked to you about this, but like we're under the ocean, so the air is weighing. So the higher you go, the lighter the air is. And so that starts pulling air through. And then also the air cools down in here, and it's hot out here, and that pulls it through even more. And so there's like some of them are just sitting directly connected to the caves, and some of them have tunnels that connect them to the cave. And the cold air gets pulled in through here and comes up through vents in the floor and travels out the windows. Like that. Okay, this is where the air, this is the area that's connected to the cave. This picture's upside down. You go down under or you go up, and then this is the room above, and there's a vent like that in the floor, a big vent. It's big. It's that big. Those are feet. Okay, and Palladio knew of these. Palladio wrote about in his big old book. And so his things are very similar. They have like a basement. This is under the earth, and then it's up, and this is cooled, and there's vents in the floor, and the cool air in the basement gets pulled up through the main living spaces. So we could do a Palladio. We can have a historical canon rethought from the point of view of one particular element. Right? So like this is half under the earth, so it's cold and there's vents in the floor. I like that Palladio would still be in it. Everyone else kicked out, but Palladio's still there. And the Villa Rotunda is the same. Okay, it has a big old cold basement, and it has vents in the floors. I don't know if I have a photo of them. Yeah, look. Right? Look at that. The big hole in the floor. So the air cools down in the cold basement with the stone next to the earth, and that's then pulled through the building by the tall dome, where the hot air creates a temperature gradient. And then, by the way, people don't really make these. I don't know. This is too simple, but it could be interesting. They're called belvederes. This is Bramante. I think it's Bramante. Maybe it's Bormini. But on a palazzo, adding this, and the loggias in Florence are about that. You know, they're about compressing the air into a tighter space so it goes faster, and then you can sit in there and get cool. Okay. By the way, I don't, this is now I want to deviate just ever so slightly. I don't know if I can do this because I don't have a thesis about this. I don't completely understand it, I have to say. But there is a deep relationship between the way in which architecture evolves in response to climate and colonialism and the history of modernity. They're very tied together in a very complicated way. This book, The Recovery of Natural Environments by this man, Alan Short, who's at Cambridge, he's very dogmatic about it. And he talks about how the climate maps, these climate maps, which is how we distinguish climates, okay, the Köppen climate maps, they were made in 1884, and then they reinterpreted. They categorize climate based on a couple of different variables, like how wet it is and how hot it is, and then they divide the world into different climate things, and they're still used. They're very useful for these things. They also, he says, are tied into a sort of a climate supremacism. Like the sense that the Western, temperate zone is the area where productive things can happen, and the people that actually, this is so interesting. He says Vulcan and Brannaman, Köppen's recent translators, felt it necessary to add the following endnote to their paper, firmly disassociating themselves from Köppen's belief. The original text has an attitude of climate determinism and racism. Environmental determinism was prominent in the late 19th and early 20th century European science. So there's an idea somehow about if we could spread the European climate around the world, we could industrialize the world. There's something like that lurking behind things. And And that is part of uh, the history here. And I don't quite know how to disentangle it, but he writes about it in that book. Um, if you want to see how he talks about it, it's very much a part of his thesis. Um, okay, and then that's 1884. Okay, so then in 1902 is when air conditioning is invented. So it was invented by this man, Willis Carrier, who was trying to dehumidify air. And the first air conditioned building is this one in 1904 um, for uh, this the World's Fair. Um, and People went in there and enjoyed it. It was like an attraction. And then in by the 1920s, okay, there were movie houses where had cooling systems in them, and they were big and expensive, and they didn't work very well because they were essentially working on the same sort of old principles, and they would just be like pumping the cold air in at the top, I think, and everyone would get very cold. Actually, they would put it in the bottom. Everyone in the bottom be freezing, and everyone in the top be very hot. And then there were more inventions. So in 1922, they made this machine, which made it much cheaper. And then in 1929, they made the first home one, which is that. There were not very many. I think only 32 were made and installed because they were expensive. And then they were made cheaper by the invention of chlorofluorocarbons, CFCs, which had a big part in the ozone crisis many years later. And then in 1932, I think is when somebody made the first affordable one. And sort of by 1947, there were 43,000 air conditioners. This is the patent for one of the early ones. And in the 60s, there were all these ads like this about how you didn't have to be hot anymore. And everyone had them. They were all over the place. And then there was the crisis in the 1970s with the energy crisis in the 1970s because of all the air conditioners. And in 1959, okay, is when ASHRAE sort of combined and became its current entity. It was originally, I think, founded much earlier, but they published the first sort of standards in 1975. And so part of the reason that things are done the way they're done has to do with many things. It has to do with the regulatory environment. It has to do with the society of engineers that publishes the standards that we adhere to. And those standards are based on certain things. They're based on a particular expectation, studies about what people's expectations for climate should be. And hilariously, I mean, it's very well known, but hilariously, all of Carrier's experiments for human comfort, the original ones, they were done on like shirtless white guys. This is a hilarious example. There's something, but it also has to do with pollution and with debris in the air and with being actually comfortable and with not getting overheated and safety and air change rates. So there's a complicated overlap of determinants going on there. Okay. Okay, before this is still the same time. So I said this was chronological. So the Casa Mila, I put this in. We could do this. We could do the Casa Mila. We could do Gaudi. Finally, everyone went to architecture school because they wanted to look at Gaudi. We never did. But this is a big climate building. It was all about health. At the time, there are big holes in it so that the air moves through it. And also, windows that open in multiple ways to get different air currents through there. And also, there's the huge chimneys on the roof, which are partially chimneys. This is hilarious. Look, it's a chimney, and it's also a, an air chimney for cool to be so it heats you up and it cools you down. They work both ways. The chimney and the wind catcher, basically, those are vents, and they go down to this little area where the chimney also is. So there's like a and the reason I put it over here is because it's all curvy inside, and I don't know what that does to air. Most things are not curvy. So looking for a curvy example, and here's one. It looks like that, or like that. I don't know. All the floors are different. Um, but yeah, you can see the fireplaces in here, and they're like big seating areas. We'd have to find them. So by the way, I wouldn't expect you to do the whole thing. When I say model something, I'm talking about like picking a room. You're gonna do like a tiny bit. It's not gonna be like a building. It's gonna be like a part, a piece of a building, like a room with a single piece of behavior. So you're not gonna ever take a whole precedent that I give you. It'd be a little area of it, and model that. Okay, that's what it would be. So this would be one room next to a courtyard with a turret in it, and that's like a little climate device, like that. Then also around this time in the 1800s, by the way, nobody ever talks about the mechanical. I've never seen an essay, I don't think there is one, about the way the wind behaves in these huge porch dominated areas. But it obviously does because this really cools the air down in these porches. And also the windows are all lined up. And there's usually, high windows and low windows that you can open differently. So definitely in these old houses, something in the shingle style, something going on there. By the way, they always have like little portals I don't think that's just to see your friend. I think it's because they want the air to move through the rooms. But nobody's ever done an analysis on these that I can tell. The Isaac Bell House, and then the famous one, Crags the wacky one that's by the ocean and very skinny. All these porches, a tunnel through it. We could pick a part of this and see if we can see how the wind is moving in there. By the way, I love this one. This is something I discovered on my own. I don't know where the heck. This is like from a 1926 Soviet competition for work like communal housing. And there's this crazy like porches and these weird messed up units that I think would be wonderful. By the way, I love this plan. This is not the one we were doing, different ones in the competition. But look at that. What the heck? Why did they do that? It's not necessary. I mean, it wouldn't make sense to do it for win. It's but it's very funny. I wonder, I might have made that up. Maybe I don't think I did. I think it's real. But okay, this is this one I think is interesting because these are double height porch spaces that connect to the stairwell, and then the bathrooms are all ganged in the middle. And it makes the bathrooms very short, and the living space is very tall. And these things are open to the outside, and then I don't know if the corridor is open. It could be very cool. Okay. All right. So that's I'm up to 1927. Okay, so basically, by the way, I missed something. I missed something very important. Well, I didn't have time to put it in, but I missed this very important milestone, but it's too complicated for us to do. But in 1884, they did a big renovation of the House of Commons, and it's like one of the first. I have all these drawings of it. It's one of the first sort of semi-mechanically ventilated buildings. It's like a semi-mechanically ventilated building, but it's done with like truckloads of ice, like big fires. And so it's just an important historical milestone, but it's all a mess. So we would never look at it. So I didn't put it in because it's not a precedent. But okay. then I want to kind of get back to the bigger story, okay, which is um, there's this book, Modern Architecture and Climate: Design Before Air Conditioning, that also talks about this narrative that I'm talking about. It's got a very it's from this 2020. It's got a very it's all about the way in which modernism was originally framed as a very flexible system. And that flexibility was twofold. On the one hand, it was about adapting to local climates. And it talks a lot about how um, uh, you know Corbusier was very interested in the sun, and how modernism was framed as all around this idea of basically um, uh, producing a machine that could go around and produce comfortable conditions in different situations. And yet there's a tension there between modernism's adaptability to the locale and its proliferation of a universal sort of climate condition on everything. But this idea that originally it was um, uh, um, it was framed that way, and then that um, sort of got taken over by air conditioning. So he says, put slightly differently, the conceptualization of the thermal interior initially developed through a careful coordination between design elements, knowledge of climatic patterns, assumptions about inhabitants' resiliency. This aspiration for achieving thermal balance was then integrated into mechanical systems and regulatory structures that were, by contrast, would seem to be universal and everywhere applicable, able to produce an identical climate anywhere and across time. In this sense, the international style, despite the suspicion with which this term is generally accorded today, was in fact quite bold and effective. Modern architecture, to a significant and underanalyzed extent, was about the delivery of a certain kind of managed thermal space, initially through design, and then as part of proliferation of air conditioning. So there's a degree to which, and Corbusier has all these drawings of the sun, and uh, people were also very admiring of Richard Neutra, who, kind of took modernism, took the Brise Soleil, and made all these sort of adapted um, uh, climactic versions of that. And there's a tension there between the capacity to use nature and use what's around locally, and also to uniform sort of bulldozer that into a single industrialized version of sort of productive commercial space. I don't know how to tease those things out, but that's both of those things are going on. And I think what's interesting is that Corbusier himself seems to me not very interested in the wind. Sort of seems primarily focused on the sun. Most of his diagrams are about the sun and how the sun moves, and the Brise Soleil, the way the sun comes in. And also Gropius made all these kind of diagrams for building spacing around the sun and around light. And um, but then I think what happens after that is very interesting, which is that um, uh, a lot of the people that worked with Le Corbusier, then sort of right after a lot of countries achieved independence from colonial rule, many of the famous architects sort of refused to do exactly Corbusian modernism and readapted aspects of modernism in very kind of innovative ways to local climates. So modernism has this moment of uh, ambition, which then sort of gets taken over by air conditioning. But somehow that's also reinterpreted by without air conditioning in a different vein throughout the 50s and the 60s and the 70s um, in other uh, more interesting ways, I think. This is here only because it's chronological, which is that uh, around the same time, Alvar, and Ino did the sanatorium for people with tuberculosis, which was one of their first six projects. It really brought them into national renown, and it's clearly all about ventilation and air, and the whole top is this deck for patients to be exposed to the air. And the whole thing is also focused around like the daily lives of people and like so it has this real strange utopian tendency to kind of manage and believe that it's achieving something healthily through the management of people's lives, which was still possible to kind of uh, feel invested in a kind of idealistic way in the 30s. So this is also such a incredibly skinny building. The way that the this super duper 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 skinny building. Uh, I don't know whether that might be interesting in terms of how it if we thicken it when we could maybe see how the state of the thinness actually impacts things. Um, and there it is today. It still exists. It's been converted into a general hospital, but it's incredibly thin place with balconies and overhangs that's trying to create air movement. Okay, I think I'm going to give you guys a break before I move into the second half here. But essentially, vernacular typologies is where we began. And I think we could stay there since that's typically what's studied. Somebody could be just interested in one of the vernacular precedents. It tends to work on a very particular typological basis in the sense of what Moneo originally said. And then modernism coming in and sort of being a precursor to uh, air conditioning. And then with this sort of very interesting relationship to climate that then gets sort of made into this uniform condition through air conditioning, but not erasing the actual climactic ambitions that were part of the movement, which get sort of interpreted in other ways. Okay, all right, let's take a break, like 15 minutes or something like that, bathroom break or something, and then we can keep going. All I'm trying to do is give you precedents, by the way, just precedents, just precedents. The only purpose of this is things to pick. We're going to deal with the math later, but today is precedent day. Only precedents, nothing else. Yes. Yes. Okay. So I was talking about this Alto project. Um, and then uh, I think just to pick up my narrative, I feel like it's kind of interesting. In the 30s and 40s, um, there's some sort of early types of passive house kind of things. Like this solar house is like the first solar energy house in 1933. And also, Frank Lloyd Wright, interestingly, sort of does figure here. Um, the Usonian houses. I don't know if you guys know the Usonian houses. They're really wonderful. I have to say, the Usonian houses are the thing that makes me still excited about Frank Lloyd Wright they're not his fancy houses for clients. They were like his very small, uh, you know, middle income houses that he believed were a type. They're a type that he designed. They have carports and they're one story. They're often L-shaped and they face the sun. And they, have a certain material palette. And they're what he imagined suburbia would be like. And they are quite delicate and small and lovely, and many of them still exist. And I think they have an enormous amount of merit as a design proposition. This is one of them, the Affleck House in 1941. This is what it looks like on the inside. They all look like this. They have a hearth. They have a very small kitchen tucked around the back. They're very narrow in plan. You go through them from the back to the front, and they're very linearly organized. But this one has this wind tunnel under it, and also has a door that can open to the wind tunnel to let like that's like a horizontal window to let air come in. So this is like a particular one that seems to go further with the idea of air. So I think I'm very interested still in the Usonian houses. They're an important part of history, and this one is a very air-driven. And actually, then this building is an important precedent. Uh, it is in Puducherry in India. It's by George Nakashima and Antonin Raymond. It's the Golconde Dormitory. Very famous. Um, and it was for an ashram, a dorm for the ashram. And Antonin Raymond was actually worked with Frank Lloyd Wright, and then went to Japan to work on the hotel there, and stayed in Japan and had uh, um, a practice there. And George Nakashima was a Japanese architect who was sent here to be the project architect for this building and actually became a part of the ashram and stayed there. And this building, there it is. Uh, very, by the way, the louvers are asbestos, so there's that. But like it's the first I think uh reinforced concrete building in India. It predates Chandigarh and all that stuff. And it's very interesting. There's a long sunken trench on the bottom, and um, it that is clearly very cool. It's shaded. Most of the communal functions, the kitchen, everything are down there. Um, and there's a courtyard back here that's got water in it, and it has and then on the other side is the sunny side, and so there's the thermal siphon between the two sides, creating a breeze through it. And there's looks like this on the inside, and there's a screen so the wind can go through the building while there's still staggered slats, so there's still privacy, but the wind can go through. Um, and then the louver is sort of protected from rain, and um, uh, the ground is all covered in you can imagine like this is all the sun doesn't reflect very much off of the grass, so this space down here stays cool. Um, and it's all covered in trees, so this side is very, very cold. It's oriented to get more solar exposure on one side. And there are the plans sections. And apparently, this is just another phenomenon. This is called temperature damping. So it's how much the temperature doesn't when it swings outside doesn't swing inside. Just an interesting name for something. And it also has this ventilated roof, precast. ventilated roofs at the top, so the air also can go up the stairways and out the roofs. And I think uh, very beautiful project. So um, there's the ashram, and George Nakashima is in the middle there. So he stayed and became part of this. So obviously, uh, everyone felt sort of good about it. So I think that's interesting because um, you know I think it's not quite the language of the international style. It's sort of an adaptation of it. Uh, to a particular situation, which is more interesting. Okay, this is another Frank Lloyd Wright. It's only here because it's chronologically displaced. Um, this is the solar hemicycle house. So just for context, uh, people a lot of this time thinking about the sun and how it would move air in buildings and how it would heat up spaces. This is sort of where that type of thinking begins. I think like the tram wall, I think all that research was done in the like 52. So like there's a lot of um you all those concepts that you hear about, they're not just like things you read in textbooks. They were sort of like the way people were testing and exploring things like at this time. And then that tram wall thing, we read about it constantly, but it's like just some guy. Like that's the thing he invented. He was interested in like thermal convection, and that's his invention. So, and Frank Lloyd Wright at this time, this house, embedded in the earth with the so it's cool in the back with the heat on the front, and then the high window so that the breeze goes through. So not scientific, not systematic, not based on anything, but trying to uh, be in touch with the natural environment. And interestingly, the same year, okay, as that is also the Farnsworth House. So very, very different ideas going on at the same time. You can see the kind of the two strains of modernism, right? This is the like, adaptability, trying to produce the thermal interior through science, through a utopian idea of science. And this is the uniform perfection sort of uh, abstraction, right? So the same exact year, it's an interesting uh, balance. I love this house. This is Kenzo Tange's house. It's only here chronologically, 1953. It's the only residential piece of architecture he ever did. But it is a synthesis of traditional Japanese typologies and modernism. So that is sort of what happens here, right? That's how a lot of architects deal with this tension, is they attempt to produce tectonic synthesis between so this is lifted on pillow tees. It's got all the tropes of modernism, but it also has the sliding panels, is based on the modular of the tatami mat. And I mean, look at that. I think that looks like a traditional Japanese house. That looks like, Corbusier did it. So like it's the same building. And I've never seen an analysis of this, but clearly it would be it would be right for that in different ways. Okay, so the other thing that happens at this time in 1947 is Victor and Aladar Olgay. They come to the United States and from Hungary, and they are the people. I don't know if you guys have heard of them. Very significant figures. They are at MIT and at Princeton, and they're very big admirers of Corbusier and Richard Neutra, and they do all of the original climate research. So they do a lot of climate research at this time, and they represent the high point of modernism as an adaptable climate oriented system. And this is their book. first book, Solar Control and Shading Devices in 1957. Um, and this is sort of like the Bible on the adaptive brise-soleil facade. And it also is the foundation for a lot of the things that you will read about like all the charts and graphs that you see in textbooks come directly from this research. And so, Christoph, who I admire a lot, is really their successor. Christoph at MIT used to teach here, refers to this book a lot, taking some of that research into the computational domain now. But the original uh, graphs and diagrams come from here. So this is the book that has all of those kind of solar radiation diagrams and a lot of the formulas for like, uh, adding, the wind from the ventilation and the buoyancy come from their research. Okay, and they did this crazy thing. This is the thermoheliodon, which was like a tank that they would. That's like an array of heat lamps, and they would attempt. It's the a very ambitious attempt to physically simulate the thermal environment, and this was part of their research at the time. And then they wrote this book, which is very important in 1963. I think only Victor Olge wrote this book, Design with Climate, the Bioclimatic Approach to Architectural Regionalism. So whenever you encounter all the projects that I will show you now, they're all bioclimatic architecture. That's the designation for this type of architecture. It's um, like an attempt to work with the local climate to achieve the best indoor conditions and minimize energy consumption and use passive heating and cooling systems before the idea of sustainability. So it has nothing to do with sustainability. Sustainability wasn't a concept. The concept that came before that was this idea of bioclimatic design, which was came about in this book. And interestingly enough, Victor Olge, I think, died in 1970 or 1972. And Kenneth Frampton was the dean, I think, of Princeton, became the dean of the architecture school, I think, at the same year. So Kenneth Frampton, very influenced by these people, by Victor Olge, and some of his ideas about critical regionalism and the idea of adapting modernism to the local situation don't only have to do with construction and tectonics, but they have to do with this idea as well. So that's the other side of modernism, from the side that became the international style and the skyscraper and the air conditioner, is the side that was represented by these people. I think there's a real, they were friends, Moneo and Kenneth Frampton. I think there's a, I don't, I think is an interesting dialogue between how typology is getting adapted or getting absorbed or getting submerged in the modern movement and the interest in the vernacular. I would imagine there's a lot of conversations about what those things mean. Okay, so then you will always see. I know you've probably seen this before, the psychometric chart. I'm going to try to show you guys some of these things, not because I want us to be invested in them, but because for me, I've had to read these things like 1,000 times in order to remember how they operate and why I should care. And I feel like without situating them slightly in a context, or maybe like not caring about all the aspects of them at once, they feel like alien and frustrating. And so I think what's interesting about these things is the way they came about, like as inventions of people to try to deal with the specific phenomenon rather than as devices that are, useful. So I think they're interesting historically, and I think by situating them historically, they are somehow a little bit more understandable. So, the original psychometric chart was for air conditioning, and it was invented by Carrier. Okay, so the first one, this diagram of graphing temperature and humidity, was because Carrier, the air conditioning guy, was interested in dehumidifying spaces. And so, like, that is what this is about. It was about a way to graph, what it does, right, is this is temperature down here. and then there's lines of relative humidity. And this is a way to graph how if you cool a space, your temperature would move around on it. I'm going to go into this a little bit more later, okay? But Victor Olgier made his own that wasn't like that at all. It was very different. And the idea was that it was supposed to be more usable for architects and more usable with passive strategy. And it just graphed temperature against humidity. And then there was an area of that they defined as the comfort zone. And that was just based on many studies. There were tons of studies. If you read Design with Climate, he lists them all. He's like, so and so said this, so and so quoted this, so and so quoted this, so and so quoted this. They don't correspond, and they won't be very good in these particular climates. I think it's only good, in North America. But since that's all the data I have, I'm going to call this the comfort zone. And then there's one for summer and one for winter, and that has to do with the fact that people wear more clothes in the winter. So the one for the summer is a little warmer because you have more clothes on in the winter, so you can deal with cold. So the lower one is the winter one, and then he drew lines, okay, on this, like, and they're very confusing. Like he drew all these lines, and the idea was if you plotted a point, like if you knew that you had 30% humidity and it was 85 degrees outside, that would be here. And then this line just says, based on their like talking to people, if you have wind at that at this 300 feet per meter or whatever that says, then that was comfortable. So basically, like if you're on a line, you need that much wind to be comfortable. And that's because if you're getting blown by wind, the air around you is a little bit cooler because it's taking away the heat that you heat up the air with. And also, we primarily cool ourselves by perspirating, and it takes away the little bit of water that is hot. So this is just like he was just saying, that was the amount of ventilation that was comfortable. And then this is kind of an important thing that I want to talk a little, just very briefly, and then I will come back to, which is humidity. We're not going to deal with humidity. Okay, it's just so incredibly complicated. We're just going to deal with air movement. But essentially, water is, if there's water and there's air, the water is like moving around. And remember, I said temperature isn't really real. Temperature is the average speed of the molecule, not the speed of all the molecules, the average kinetic energy of the molecule. So it's just a global averaging of how fast all the molecules are moving and how that feels to us. Then if you have molecules at the interface, some of them are going faster, some of them are going slower. And if they happen to be going faster, they will evaporate. That's why things evaporate when they're not boiling, because some of the molecules are going faster, and if they're at the interface, they will vaporize, turn into air molecules. And then likewise, some molecules are always condensing because they're going slower, so they're condensing. So there's always an exchange between some molecules evaporating and some molecules condensing. And there's water vapor in the air. And when water evaporates, it takes a certain amount of energy to evaporate. And so when you have spray water into the air, the water in the air evaporates. That takes amount of energy, and that energy is essentially hidden. It becomes what's called latent energy, and then it cools down the air because it took some of the energy to evaporate. So you can cool the air just by spraying water in, because then the water evaporates and that takes energy out of the air. So essentially, evaporative cooling is just like an air conditioner, except it also humidifies. You just spray water into the air evaporates, the water evaporates, vaporizes. As it vaporizes, it takes an extra amount of energy to vaporize, so that heat becomes part of becomes no longer feelable. And so when you talk about like something blowing over water or blowing over like a lake or blowing through a fountain, that's what's happening. It's just some of the water is evaporating, and that cools down the air. And the maximum amount that the air can cool through evaporation um, is what's called the wet bulb. So the dry bulb the coolest the air could be through evaporating is what's called the wet bulb temperature. Um, like if the air was complete, if you filled the air with water, it would get cooler. And so it's sort of confusing. But if you think about it, you could, if you had a really good swamp cooler or a really good fountain, it would just cool the air until it was like full of water. And that is the wet bulb. And so what's happening is also, okay, is the air hits the water and exerts a pressure on the water. And the water molecules in the air are bouncing around and hitting the air, and they're exerting a pressure on the air. That's called vapor pressure. The pressure of the air molecules, the evaporated water molecules on the air, is called vapor pressure. And so sometimes air has like a thick, kind of swampy feeling and you feel the pressure of the vapor in the air. People don't like it. It's kind of uncomfortable. And when the air is completely saturated, and the vapor pressure, this is called what's 100% vapor pressure. Okay, so when the air gets completely saturated, what happens is there's enough water molecules bouncing around that they will start condensing at the same rate as the ones that are evaporating, and then it gets into a balance, and you can't get any more water in the air. Just because the ones that are coming out of the air, there's enough of them that the ones that are coming out of the air match the rate of the ones that are evaporating, and no more can evaporate. And that's temperature dependent, right? Because if it was colder, more would be condensing, and so it's temperature dependent. Okay, and that's why you can boil things at a cold temperature, because if you put it in a vacuum, there's no air pressure, and so all of the water can just vaporize. Usually, the air is pushing down, and so the fast molecules down here can't turn into bubbles. Only the ones on the surface can bubble and evaporate. But if it's in a vacuum, there's nothing pushing down on the water, and so any fast molecule down here can vaporize, and then boiling can happen automatically at any temperature. So boiling is when the vapor pressure matches the air pressure. Okay, and so that is measured with a sling thermometer. So you have something here that's covered in a wet cloth and something here. You spin it around, and this evaporates as fast as it can. And the difference between them is this is the wet bulb temperature, and that's the dry bulb. I'll go over this with you later, but we can very easily plot things on Victor Olgay's chart and see whether or not you can cool it by whether you can be comfortable by blowing air over yourself. And that chart is outdated. And then what happened is it was updated by this guy Giovanni in 1969, and then it was updated again in 1979. Giovanni in 1969 took Victor Olgay's ideas and applied them to the original psychometric chart, and then they kept updating it and adding more things to it. And so all these regions are just this dude's interpretation based on available data, like for when you would be comfortable, like if such a thing was going on. Okay, so you just plot a point, and then you refer to Giovanni, and you find out whether or not you're comfortable. Okay, and then all of that was digitized in 1979 uh, in this program, the Climate Consultant, the first one. So you can download it in 1979, and you can you can load start a new project, and you can load an EPW file, and you can load an EPW file, and it'll give you all those charts that you see all the time. Ladybug is the same. This is where it comes from. So, like, this chart was the latest version of the sequence that went through like that historical development. So basically, um, the uh, um, air conditioner guy made the first one. Then Olge made his own. Then Giovanni merged the two, and then they digitized it and kept adapting it. And the one in Ladybug, okay, Ladybug and Climate Studio use the U.S. Department of Energy's algorithms for calculating these things. So they all refer to the same underlying data structure. So I think that what's important, okay, is just two things. One is that is just to understand that how hot it is the dry bulb, and how cool it could be with water is the wet bulb. And you can plot those things monthly, and you get that interesting diagram that can tell you whether or not it's nice to be there at that time. You can plot it with Climate Studio. I don't know if you guys know how to plot it. I'll show you. But like, you can plot it with Climate Studio, you can plot it with anything. And then also these comfort charts that show you, I only want to think about when natural ventilation is comfortable. I don't really want to think about it, but like they are just an interpretation historically that was based on studies of people in a particular situation, multiple studies, somebody trying to, pull that information together and plot it on a chart. And it's not like it's taking into account any information about your project. It's just saying, if it's this warm and this humid, if you had this much air based on the standard, you would be comfortable if you're one of the people in the study. That's what it's saying. And so there are guidelines to help architects attempt to figure out whether a particular solution might possibly be useful in their situation. And they're useful because you can look at it and be like, maybe that would be worthwhile, or maybe it's totally out of the ballpark. But other than that, it doesn't tell you anything. And that bubble never moves. It's always the same bubble. I think it's confusing. You look at it, you think maybe if I graph it, it'll be a different place, but it's not. It's just that's the bubble for like cooling down by air. Okay, and they've been changed over time. ASHRAE had their different studies by different people. There's different versions of the chart based on different studies, but it's not based on your project. It's based on only the studies and the relationships between how hot and how humid the air is. Okay, so that was going on at this time. Okay, by the way, I love this piece of art. That's an air conditioner. That's a swamp cooler. Just a bunch of water with wind blowing over it, and then the air evaporates. The water evaporates and takes energy out of the air. Okay, so all this stuff was the attempt in the 1950s and the 60s to start to produce standards for how people would be comfortable. And that's useful in the sense that it tells us something about how to work passively in different climates. And it's strange in the sense that we have a standard that we're referring to. So it's both incredibly wonderful and incredibly odd, right? Okay. Yeah.
Like a lot with wet bulb temperatures and like climate change. And they talk about like a certain heat, like once the wet bulb temperature is above a certain amount, like that's like then it's like too hot for living things because
Yeah.
So is that the same concept as why like it will boil? I don't know if it like if your body temperature is the same as the wet bulb temperature, then your
Well,
sweat.
if the air is 100% saturated with air, you can't sweat. And so the way that you typically cool, the way we don't think we're sweating, but we are, like the way your body maintain basically your body has a core temperature, and the way it doesn't overheat is by, producing moisture, and then the moisture evaporates, and that takes hot air, it takes temperature out of your body. So if the water can't evaporate, very dangerous because your body's cooling mechanism doesn't work. So you can easily overheat. So if the air is really, really humid, your sweating mechanism stops working, and then you have no way to cool yourself down. It's dangerous. So like um uh yeah. Does that make
Yeah.
sense? Yeah. Okay. So I don't know why I'm showing this. Uh, Charles Correa went to University of Michigan and studied with Buckminster Fuller. I just think that's interesting. He was very, very, very interested in the wind. Did this tube housing, which is supposed to be affordable, low cost housing uh, for that was entirely naturally ventilated. And I kind of like this diagram because there's actually different ones that show different ways of using the house with people living in different kind of conditions. There it is. Resting, heating, parents, grandparents. I think that's sort of nice. Uh, and there's a lot of CFD analysis of this, so useful if to see whether our stuff is working, right? So I think it's an interesting uh, very, very didactic precedent. But what's also kind of cool is he made another one that's like a rich person's one, which is almost the same exact house, but scaled up. Um, there's the upper floor and there's the lower floor. And it I don't know if it works on the same principles, but it kind of seems to attempt to, right? Has sort of like double height spaces and vents and overhangs. And then what's also interesting about it, by the way, is it was made in 1964, and so was this. So there's a formal sort of interest there. Look at that. Isn't that amazing? The same exact year. Okay. So um, I like it because I think that um, we don't I like the idea that we're not just leaving architectural history and going off on some tangent. I like the idea that the people doing these things are only kind of doing it also with formal desires. And so somehow there's like an architectural desire to reproduce the postmodern image through the medium of the wind. I find that interesting. Um, okay. Um, this person is really, by the way, there's another Charles Correa that I put in here, but it's later. So this is chronological. This person, not this building. I just put it here because I like it. Just an example of his work. I don't know if you know this guy, Van Molly Van. He's a Cambodian architect. Molly Van is his last name, and Van is his surname, but it said Van Molly Van when they're together. But if okay, like, but if you were going to call him, you're going to say, "Hey, Molly Van." That's what you wouldn't say, "Hey, Van." And so anyway, he like was very important in Cambodia, like so incredibly prolific, like incredibly, incredibly prolific. He studied with um, uh, uh, Corbusier, I think. He went to France in 1946 and studied there, and then he came back the year of independence in Cambodia, and he was sort of responsible for building uh, the whole infrastructure of the country at the time. And his architecture is sort of called the Khmer architecture tradition. And he was sort of interested in combining modernism with the original Cambodian sort of uh, by the way, this is Angkor Wat, and this is a really interesting thing because there's so many like it's all surrounded by water. This whole universe of like canals and the relationship between air and canals and the way things get wet. And it's like considered like the first hydraulic city. Okay, so Molly Van's architecture is all about the relationship of wind and water in modernism, drawing from those two things together. This is his National Olympic Stadium. I think it's kind of crazy looking, amazing. There's a moat around it, okay? And like with those incredible water tubes, and then like the seats are porous and the air goes in, right? I mean, have you guys ever seen this guy before? Really, really beautiful stuff. And then there's this one, okay? The Institute of Language. There's a double layered ceiling here. Wind blows through here, and air can get pulled out by virtue of this thick tubular ceiling. And also it's another lifted up project. Um, uh, like that. And it's very sad because he had to leave. There was, he said by the end of the 1960s, all the structures were in place for, the capital to become a great city. And then there was, a extraordinary amount of violence in the 1970s, and Cambodia kind of could have become like Singapore, and then it was suffered a lot of violence, and he had to flee, and all of his work had sort of like fallen into disarray. But actually, there's a lot of attempts to document it, and Nancy was part of this attempts to document it, so she knows a lot about it. So I think these two projects, I find them really quite beautiful and stunning, and I think we could look at how the wind moves in them. All of his architecture is really about the wind, and his other projects are too, but I just happen to like those. Okay, then there's Sea Ranch. This is around, these are in the like that one's 72, this one's 63, 64. So the same year as Sea Ranch, 63, 65. Um, so Sea Ranch was like a utopian community made by Berkeley faculty members in 1964. Charles Moore was sort of one of the main architects there. And they made a community that was supposed to be based on ecological principles. And they had all these tenets, like you're not allowed to block anyone else, and you're not, and everything has to be made of certain materials. There's no air conditioning. You're not allowed, there's no washing machines. You dry your clothes outside. You can't have any certain kind of plants. And a lot of the early homes are very small and very architecturally significant. And actually, it was kind of strange because today it's like a Silicon Valley holiday house. And in the 1970s, there was a legal issues about this because they were, this utopian community was like taking over what used to be public land and turning it into private property. So there was a lot of regulations put into place about what you can do with California coastline, which are still like, in place because of Sea Ranch. So oddly, the utopian project is sort of has a strange destiny, but the early things are rather architecturally significant. It's interesting if you want to rent a house at rent a home in Sea Ranch, they have all these like guidelines for how you can stay comfortable. They say, at night you should, open the back door, and in the morning you should close the shades so that it doesn't heat up, and you can close the shades but keep the windows open so that the sun doesn't heat up the air, but the air still moves through. And like you can, like in the evening, the breeze shifts, so you should get like the breeze from the sea that comes in at 4 o'clock, and that'll keep you cool. And so like there's all of this like operating of the house that like makes it sort of function. Um, and it is also like interesting, I think, because they do have, this is the first one, this is the famous one, Condominium One, Charles Moore's. Uh, Looks like that. There's like a bathroom up here. I like this because if you imagine the hot air from the bathroom would create a thermal current rising up there. Um, and very tall to let hot air. And also they have all these curtains with open screen windows. So very ripe for seeing how the wind might move through it. There are the drawings. That's Charles Moore's first one. And then there's also his later one, the Rush House, which has this extremely tall chimney uh, in the space, and all of these as well. And then there were also some very little ones there for a while that were really quite affordable and interesting. Um, the new ones are kind of horrific, but like they look like it, but they don't feel like it. But I like those little ones. They were some that were very small, which is cool. That's the rush out. That's the plan. You can see the tall chimney. There it is. I think I showed that image already. Okay. All right. Then there's Jeffrey Bawa. Jeffrey Bawa, Sri Lankan architect. So you can see the trend here, right? These are all the people that studied in the West with like Corbusier, and then they were like and then they adapted their modernism in a very creative way to the specifics of where they were from, and also were unwilling to accept the formal language of modernism. They wanted to transform it as a way of escaping the impression of colonialism. So there's like a formal impetus as well, which is like refusing to take the language, refusing to take Corbusier's forms, and using the climate, using um, the traditional vernacular to reinvent the formal language as well. So very Bawa stuff is. I think that plan is wild. I don't think we should deal with that. That's his own house. Um, uh, he's the most famous person from tropical modernism. Uh, but uh, but he also did a bunch of offices. This is his own house. He also did offices, which are less well known. This is the state that he designed. We could clearly analyze that, but he also, I love that. Oh, God, it's fun to just repair, but very beautiful. Um, uh, I also think that's cool. Remember, I talked about the grain silos? That's that. That's actually porous. So this is the only one that I know that is like a really, all of his projects have these like very interesting like attempts to make technically operative naturally ventilated facades. And the degree to which they're successful, I do not know. I think they're not always successful, but they're sort of interesting. Um, and I think that one's cool. But also he did this building, which is like the first and maybe only naturally ventilated high-rise office building. And it has this crazy window where like this blocks the rain and this takes the air up high, and then there's air that comes in here and comes up, and then you can also open the windows. Wild. Like it was really like, by the way, this building uh yeah, this was 1971, 1978. So no air conditioning. It's air conditioned now, which is very sad. And it doesn't work that way. But the stairs are like ejected to the facade so that they could be naturally ventilated. And the whole thing was like this open plan, and it's made in this shape to like an airfoil, so the wind sort of like scoops around it. Um, and there's doors into the like in the Frank Lloyd Wright house, so that the wind you can open and the wind comes through. By the way, the occupants apparently hate it. Like the papers blow around. Like you can't work in there. And and very quickly after this, like the city became much more dirty, and so like it was a problem. I think cars came, and so like it screwed it up. So it's kind of like a failure, but still, still it would be amazing to see it. I feel to see what it would be like and try to imagine how it operated. Um, by the way, I like this project. This is Casa this is by like a Spanish architect, Luis Peña Ganchegui. This is also 1964. We just did 1964. That's why we're here. But I think this is clearly a naturally ventilated project by the wind. Got this kind of garden in the middle that's heating up. But also the reason I put him in here is he did this comb of the wind. This is the most famous thing with Edward Chalita. So he clearly cared about the wind. Edward Chalita did those sculptures and he installed them here. Okay. And then Balkrishna Doshi, uh, who is also an Indian architect, also worked with Le Corbusier, also worked with Lucan. So he's quite a pedigree. I think also won the Pritzker Prize very recently. There he is with Lucan. Um, but he has a very beautiful. I like this, by the way. I don't. This is his first project that he did independently in 1959. But I remember seeing this. I was in Bogota and we saw there was a stair just like this, and it was very breezy. Like it was under a building. I don't think it's a famous thing, so I couldn't find it. But under a building, and you step up. Like there was this patio down low, and the land is up here, and you step up, and because it's getting skinnier, the whole thing is cool, and you go under there like to eat lunch. Very nice. Um, he also did this crazy thing later in life, which is like an installation with an artist. But he has this beautiful school, a school of architecture, um, which has like a funnel for wind under it and these big doors. So I think, look at that. There's a wind shaped thing if I ever saw one. So and then that space looks very windy. So I thought that would be cool to analyze. This is clearly crafted by the wind, and also he did this township, Easel Township, outside of Hyderabad, and this is also um, uh, um, designed to be windy. It's based on the wind angle, so they move through the buildings. So interesting to see if that works and how that operates. Back to Charles Correa, he did this one. I know that people don't like this building, but still, what a section! Yes, right? God damn! Look at that. That is a section. I'm always so thrilled by that. I can't help myself. I just want people always say it's just clearly he just wanted to make form with the wind. Clearly it's formally driven, but still exciting. And it is based on there's all these different units and it is based on the sea breezes. And so I thought we could take one of those units and analyze it. Um, it's uh, there's supposed it's the best version I think I if you think about it right like this is like the unité de habitation but way better. It's like the wind version of it. The unité de habitation is like the sun version, and this is like the one that the air actually moves through. So I feel like we could do that. Somebody should do that. Okay, then also Paulo Mendes de Roca is a Brazilian architect, also won the Pritzker Prize. Uh, he only built in Brazil, I think, for the most part. He's part of the Paulista school in Brazil, which is all doing things with concrete, but also they didn't like brutalism. They were like, we're not brutalists, but they only made things that look brutalist. But they were friends with Lina Bobardi, but she wasn't one of them. But he this is his house, which is clearly by the way, there it is. That's it. That's where it is on Google Maps. I found it. It's called you have to look up the Butanta house, and it doesn't say it very easily, but um there is this crazy window and these overhangs and an undercroft. So I'm sure I mean, it's clearly about the breezes. Um, and he also did this, which is a kindergarten. It's like a play space for a kindergarten. And I cannot imagine how windy it is in there. So I thought if we're looking for something outdoors, that seems exciting to me. Look at those vents, those things that block the breeze and kick it up at the ceiling. Thought that was cool. Um, and then like some of his other people like are even more all about it, his friends. This is Decio Tozi. This is like that's the diagram for it. So this I didn't have an interior of it. I didn't find one, but like there's many. But there's the wind just like goes in here and goes under and ah bouncing around. So I don't know. Interesting, strange precedent there. Okay. And then what is this? Oh, I've shown this to you guys, some of you guys before. I really like this building. This is also Paolo Mendes de Roca, the Edificio Jagura. He's done this twice. This is the one that I like better. And it has this incredible situation where the kitchen is dropped to make a clerestory. So that the unit is on two levels, and the back is all it has that vent high window, so the smells get blown through. I think it's quite stunning. So we could we could look at that one. Um, and that also, like the Unite, by the way, the Unite is not the first one to have this thing. The first one to have it is also from the damn Russian competition. Look at that. Okay, so I thought that was cool. Some kind of closure for us there. Okay, so then, by the way, I'm running out of time. I realize. I'll try to wrap it up. But like this is also an interesting time period. Okay, finish my story. This is an interesting time period because in the 80s, we're now in the 80s, there was this solar movement and people interested in solar the way the air would move in solar driven houses, but they didn't um like deal with natural ventilation. It's just the air moving around in these heated houses. And there used to be these magazines that like this that look very like Earth Day-y. This is from when I was born, like around this time period, this sort of like investment in the sun pre the environmental movement. Okay, I like this building, but it's out of place. Very interesting, breezy corridor. Okay, so then in 1985, okay, is when people became aware of the ozone layer hole that was made by the CFCs and the HFCs. And so they were worried about air conditioning. And also in 1988 is when James Hansen testified to Congress about the climate crisis. That became sort of public general knowledge. And so then right after that, you see all of these extremely like techie projects in the 80s where people are like trying to do like fully natural ventilated buildings with like wind turrets and things like that. And they're crazy. Like to try to get it to work is like not like it's like like it's just very hard to get a classroom building to work with like all of this like the technology is like yes. And then the other one, the famous one, this huge library, Lanchester Library, Coventry University. Uh, they said there's a funny quote about it. Uh, they say this is the world's first deep plan multi-story naturally conditioned building. The physics is complicated. The physics there are simple the natural air conditioning is achieved by principles that are simple, but the physics is very complicated. It looks like that. Ooh. And then also the Reichstag Dome in 1993, which has air comes in the back and goes into this plenum and then is heated by people in the thing and lights and then drifts up through the dome by Norman Foster. Uh, by the way, this one has not been analyzed by natural ventilation. This is a Herzog de Meuron house, but it looks like a natural ventilation precedent to me. There's a big tunnel through it. So that seems like a cool possibility to me. It's a very famous house. I think it's their best house, but it's not been analyzed that way. Then there's this. I'm wrapping up. I promise. There's this end. There's a return here. I think. Okay, which is that I feel like people start rather than the techie thing. I feel like you see some kind of like an attempt to use the vernacular in the way that it's supposed to be. So this is this uh, architect. Uh, uh, his name he's usually just referred to as Lile. Um, and he does all these precedents that are all these attempts to refabricate to interpret the shed roof from the point of view of wind, like that. But I think that one's icky. But that one I think is very beautiful. This is a hospital. And it's a naturally ventilated hospital. I think it's quite beautiful. It has all these like deep verandas and high windows and things like that. This is also in Brazil, and people have done. Look at that! It's a plexiglass one in a wind tunnel. Okay. So very pertinent, and we can see how other people have analyzed it. And this one has like a tunnel in it, so it's also got the ground sink in it. And then DeVito Francis Carey, right, who just won the Pritzker Prize very recently. His projects are like an essay in different ways to use the wind. I think like every single one. This one is a thermal one, like that, but like every single one of his projects is like a different version of natural ventilation. So like they're really, it's like a catalog of every single technique uh, used again. So um, I think, uh, there's a sort of a simplification from the projects that you see in the 80s and 90s, and sort of a rediscovery uh, of the vernacular type form, which I have to say makes me wonder whether or not we have types again, or at least in a way, like we might have uh, some connection to them that maybe we didn't have for like several decades in the middle. Although I think that would be a very controversial position. And I also think what's beautiful is that um, I feel as though I feel as though the wind itself has its own canon, and that canon is somehow like that way of looking at the world uh, reveals different connections between different parts of the world and different sort of similarities that maybe you don't see if you just look at form. Okay, so what I want you guys to do, I know we're out of time, but what I want you guys to do is decide on a precedent. You can pick anything that I showed, or anything by the architects that I showed, or if there's something else that you like, it's fine too. But and pick a part of it and run it by me so that you don't go down a rabbit hole. And then you can start to model like a simple version of that that you can study when we get into simulation and wind tunnels. And then also, I will keep uploading all of the um, essays. So I think you don't have to read all of them, but you can, if there's one that pertains to what you pick, you can look at how somebody else did it. And I am also, as soon as class ends, I'll post a sign up sheet and we can um, uh, you don't have a desk, do you? You're done. Yeah. So um, I we will distribute materials. Why don't you sign up and then like I will um, uh, maybe I'll come to school on Monday or something and hand out materials or something like that, and we can have uh, a short meeting about how to um, uh, begin to test the joints and thicken things. Okay, excellent. Thank you guys.